Hello everyone and welcome. I'm Professor Diwa, back with another math video. In this video, I'll be going over Introduction to Functions. Our objectives: define relation, domain, and range, identify functions, use the vertical line test for functions, use function notation. Alright, so let's get started. First, we're going to go over the definitions for relation, domain, and range. The definition for relation states, a relation is a set of ordered pairs. Next, we have the definition for domain. It states here the domain of the relation is a set of all first components of the ordered pairs. Finally, we have the definition for range. It states here that the range of the relation is a set of all second components of the ordered pairs. Now let's look at the diagram below. In the diagram below, we have two sets. Set A, which is composed of the numbers 1, 2, 3, and 4. Set B, which is composed of the letters A, B, C, and D. Now between these two sets, we have arrows going from set A to set B. This sets up a correspondence or a relation between set A and set B. We have 1 corresponds to A, 2 corresponds to B, 3 corresponds to C, and 4 corresponds to C. We can represent this correspondence or relation as a set of ordered pairs. So on the left, I have a set of ordered pairs. I wrote curly brackets, and then inside the curly brackets, I have my ordered pairs. 1, A, 2, B, 3, C, and 4, C. The domain for this relation would be the set of all first components of the ordered pairs. So we would write this out using a set of curly brackets, and inside the curly brackets we write 1, 2, 3, 4. Next, the range of this relation would be the set of all second components of the ordered pairs. So we can write this out using curly brackets, and then inside the curly brackets I have A, B, C. Notice here that I did not list C twice in my range. If a value or a letter is used more than once in your ordered pairs, you would still only list it one time in your domain or range. For example number 1, determine the domain and range of each relation. For part A, we have the set of inputs, which are cities. We have Lubbock, Colorado Springs, Omaha, Yonkers, and Sacramento. Next, we have the set of outputs, which is population in thousands. We have the numbers 307, 195, 404, 35, 445, 206, and 197. We have a correspondence or relation that's set up between each of the cities and population. Lubbock corresponds to 206, Colorado Springs corresponds to 307, Omaha corresponds to 404, Yonkers to 197, Sacramento to 445. First, we write out our domain. We use a set of curly brackets. Inside the curly brackets, we have Lubbock, Colorado Springs, Omaha, Yonkers, and Sacramento. Finally, we have our range. We write it out using a set of curly brackets. We have 307, 404, 445, 206, and 197. Notice here for the range, I did not include the numbers 195 and 35 because the correspondence or relation didn't use those values. Moving on to part B, we have a graph with the plotted points of -2, 3, -1, 0, 0, -1, 1, 0, and then 2, 3. The domain for this relation would just be all of the x values that are used for each of the points. If we take a look at the x-axis, you could see that we use the value of -2, -1, 0, 1, and 2. So we write the domain out using a set of curly brackets, and then we list the numbers as -2, -1, 0, 1, and 2. The range for this relation would just be all of the y values that are used for each of the points. So if we take a look at the y-axis, you can see we use the value of -1, 0, and 3. So we write out the range with the set of curly brackets, and we just list the numbers -1, 0, and 3. Moving on to part C, we have the relation represented by a set of ordered pairs. We have the first ordered pair as 2, 3, and then we have 2, 4, 0, -1, and finally 3, -1. To write out the domain, we just list all of the first components of each of the ordered pairs. So I wrote out a set of curly brackets, and then I have 2, 0, 3. For the range, we just list out all of the second components of each of the ordered pairs. So I wrote out a set of curly brackets, and then inside I wrote 3, 4, -1. Alright, so now let's move on to part D. For part D, the relation is represented by the graph of a line. The equation for this line is y equals 2x plus 1. Notice here that we have a solid line that goes infinitely towards the left and infinitely towards the right. This means that we use all of the x values that are listed on the x-axis. Also, this line goes infinitely up and infinitely down, which means that we use all of the y values that are listed on the y-axis. So for both our domain and range, we would not be able to list out each of the values one by one because there's an infinite number of them. What we're going to do is use interval notation to represent our domain and range. For the domain, we write parentheses, -infinity, infinity, close parentheses. And for the range, we write the same thing. We write parentheses, -infinity, infinity, close parentheses. Next, we're going to go over the definition for a function. It states here that a function f from a set A, which we refer to as the domain, to a set B, which we refer to as the range, is a relation that assigns to each member of the set A exactly one member from the set B. So this definition is very specific on what makes a function. In the next example, I'm going to show you how we apply this definition to determine if a relation is a function. For example number 2, determine if each relation is a function. For part A, under domain, we have the numbers -1, -2, 0, 1, and 2. Under range, we have the numbers 5, 6, 7, and 8. The correspondence between the domain and range, we have -2 going to 5, -1 going to 8, 0 to 6, 1 to 6, and 2 to 7. To determine if this relation is a function, we just need to check that each member in the domain is assigned to exactly one member in the range. So -2 is assigned to one member in the range, which is 5. -1 is assigned to one member in the range, which is 8. 0 is assigned one member in the range, which is 6. 1 is assigned to one member in the range, which is 6. And 2 is assigned to one member in the range, which is 7. So each member in the domain is assigned exactly one member in the range. This matches up with our definition of a function. So yes, this relation is a function since each member in the domain is assigned to only one member in the range. For part B, the relation is represented by a graph with several points plotted. Each of the points have their corresponding coordinates. So one point is at -3, 2. The next point is at 0, -2. Another point is at 0, 3. We have another point at 1, 5. And finally, our last point is at 6, 6. Next, we need to determine if this is a function. Well, if you take a close look, notice at the point 0, 3 and 0, -2. The x value of 0 corresponds to two y values, 3 and -2. So this means no, this relation is not a function because 0 has two outputs in the range, 0, 3 and 0, -2. Moving on to part C, our relation is represented by an xy table. Under the x column, we have 2, 33, 4, 5, and 2. Under the y column, we have 11, 10, 5, 1, and 8. So 2 corresponds to 11, 33 corresponds to 10, 4 corresponds to 5, 5 corresponds to 1, and 2 corresponds to 8. Next, we need to determine if this relation is a function. If we look at the x values of 2, you can see here that 2 corresponds to 11, and 2 also corresponds to 8. So we would say that no, this relation is not a function because 2 has 2 outputs in the range. We have 2, 11, and we have 2, 8. Moving on to part D, we have a graph with several points. We have a point at -2, 3, another point at -1, 0, another point at 0, -1, another point at 1, 0, and finally we have a point at 2, 3. Next, we need to determine if this relation is a function. After looking at each of the x values and their correspondence, we can say that yes, this relation is a function since each input has only one output. Moving on to part E, we have that our domain would represent the people in a classroom. Our range is represented by a letter grade A, B, C, D, or F. And then our correspondence is a grade that a student or a person receives on an exam. So we need to determine if this correspondence or relation represents a function. I would say yes, this correspondence is a function because a person in a class can only receive one grade on an exam. Moving on to part F, the domain are members of an orchestra. The range is the set of instruments, and the correspondence or relation is the instrument a person can play. For part F, I would say no, this correspondence is not a function because a person can play more than one instrument. For example number 3, determine if each of the following relations are a function. For part A, we have the equation x squared plus y equals 1. To determine if this equation represents a function, what we're going to do is first solve for y and test out a value of x. So first let's solve for y. To solve for y, we subtract x squared from both sides of the equation. After doing the subtraction, we get y is equal to -x squared plus 1. From here, we need to pick a value of x, plug that value into our equation, and see what we get out for y. So let's take x equals 0. Plug in 0 for x in our equation, we get y is equal to -0 squared plus 1. Simplifying this, we get that y is just equal to 1, and this means that 0 only corresponds to one y value, which is 1. Yes, this is a function. Moving on to part B, we have x equals y squared. For this one, we're going to follow the same process. We're going to solve for y, and afterwards we're going to test out an x value. To solve for y, we need to get rid of the square. To do that, we just square root both sides. So I have the square root of x equals the square root of y squared. Simplifying this, we get y is equal to plus minus the square root of x. From here, we could go ahead and plug in an x value. So I'm going to use x equals 1. Substituting in 1 for x into our equation, we get y equals plus or minus the square root of 1. This is equal to positive and negative 1. So this means our x value of 1 corresponds to the y value of positive 1 and the y value of negative 1. So our final answer here is no, this relation is not a function. Next, we have a practice problem for you to try. Determine if each of the following relations are a function. For part A, we have the equation x plus y squared equals 1. For part B, we have the equation y minus 4x squared equals 36. Alright, so go ahead and pause the video, try out this problem, and then check back with the video to see the solutions. Alright, so let's get started. For part A, we need to solve the equation for y. So first, I'm going to subtract x from both sides of the equation. After doing the subtraction, we get y squared equals negative x plus 1. From here, we need to get rid of the square on the y. So we take the square root of both sides of the equation. We get the square root of y squared is equal to the square root of negative x plus 1. Simplifying both sides, we end up with y equals plus or minus the square root of negative x plus 1. Next, we could pick a value of x to test. I chose to test the value of x equals 0. So we plug in 0 for x in our equation. We get y equals plus and minus the square root of negative 0 plus 1. Simplifying this, we get y is equal to plus or minus the square root of 1, which is equal to plus and minus 1. So this results in two ordered pairs. Because 0 corresponds to two different y values, 1 and negative 1, this means no, this relation is not a function. For part B, we need to solve for y. So first I'm going to get rid of the minus 4x squared by adding 4x squared to both sides of the equation. After doing the addition, we get y equals 4x squared plus 36. From here, we could go ahead and plug in a value for x. I chose to use x equals 0. So plugging in 0 for x in our equation, we get y equals 4 times 0 squared plus 36. Simplifying this, we just have y is equal to 36, so we get the ordered pair 0, 36. Because 0 only corresponds to one y value, this means that yes, this relation is a function. Next, we have the vertical line test. It states here, if no vertical line can be drawn so that it intersects a graph more than once, the graph is the graph of a function. So the vertical line test is just a visual test which is pretty easy to apply. I'm going to show you how we apply this in the next example. In example number 4, which of the following graphs are functions? For part A, we need to apply the vertical line test. So you can see here that I have 3 vertical lines crossing the graph, and they only cross the graph only once. Because it's not possible to draw a vertical line crossing any part of this graph more than once, this means that yes, this graph is a function. Moving on to part B, you can see we have the graph of a vertical line. Applying the vertical line test to this graph shows you that we would just have a vertical line on top of another vertical line. These two lines intersect each other at every single point. So this means that no, this graph is not a function. Moving on to part C, we have what's called a piecewise graph. It's important that you know what it means when we have an open circle and a closed circle on a graph. A closed circle on the graph means that we actually include that point as part of the graph. An open circle means that we don't actually include that point. So no matter where we draw a vertical line on this graph, we would actually only cross it once. Even in the middle where it looks like we crossed twice. Remember that a closed circle means that that point is included, but on the bottom, notice here that we have an open circle. That means that that point is not included on that part of the graph. So a vertical line going through this part of the graph only crosses once. So yes, this graph is a function. Moving on to part D, again we have another piecewise graph. And no matter where you draw a vertical line, you would only cross the graph once. So yes, this is the graph of a function. Moving on to part E, again we have another piecewise graph. And you can see here, no matter where you draw a vertical line, you would only cross this graph once. The only part that may be questionable is right there in the middle where we have 2 open circles. But remember, the open circle means that we don't include those points as part of the graph. So really, drawing a vertical line through those 2 open circles does not cross the graph at all. So yes, this is the graph of a function. Moving on to part F, we have the graph of an ellipse. You could see here that I drew a vertical line crossing the graph more than once. So that means no, this graph is not a function. Next, we're going to talk about function notation. To denote that y is a function of x, we can write y equals f of x. This notation means that y is a function of x, or that y depends on x. For this reason, y is called the dependent variable, and x is the independent variable. Note here that f of x can also refer to a y value. For example number 5, Find each indicated function value. For part A, we need to find f of 5 for the function f of x equals 3x plus 2. So note here that f of 5 refers to the y value that results when you substitute in 5 in for x in the equation. So what we need to do here is find the y value associated with the x value of 5. We just need to substitute in 5 in for x in the equation and then simplify. So we get f of 5 is equal to 3 times 5 plus 2. Simplifying, we get f of 5 is equal to 15 plus 2, which is equal to 17. So f of 5 is equal to 17. Moving on to part B, we need to find g of negative 2 for the function g of r equals 5r squared plus 3r. To find g of negative 2, we just substitute in negative 2 in for r and simplify. We have g of negative 2 equals 5 times negative 2 squared plus 3 times negative 2. Simplifying this, we get g of negative 2 is equal to 5 times 4 minus 6, which is equal to 20 minus 6, which equals 14. So g of negative 2 is equal to 14. For part C, we need to find h of 4 for the function h of x equals 11. Notice here that this function doesn't have an x variable in it. We just have 11. So that means we can't plug in 4 in for x. So all we need to do here is write h of 4 is equal to 11. For part D, we need to find capital F of a plus 1 for the function capital F of x equals 2x minus 7. So we just need to substitute in a plus 1 in for x. Doing the substitution, we get capital F of a plus 1 is equal to 2 times the parentheses a plus 1 close parentheses minus 7. To simplify this, we distribute the 2 inside the parentheses to the a and the plus 1. We get that this is equal to 2a plus 2, and then we bring down the minus 7. Simplifying this further, we get that capital F of a plus 1 is equal to 2a minus 5. Moving on to example number 6, find each function value by using the graphs of f and g. For part A, we need to find f of 4. Now remember that f of 4 represents the y value. Specifically, we need to find the y value that's associated with the x value of 4. To find this y value, we just go to the graph of f, we look for the x value of 4, and we could see here that 2 is associated with the x value of 4. So f of 4 is equal to 2. For part B, we need to find f of negative 2. So on the graph of f, we go to the x value of negative 2, and then you could see here at negative 2, the y value associated with negative 2 is positive 1. So f of negative 2 is equal to 1. Moving on to part C, we need to find g of 5. So we go to the graph of g and find the x value of 5. From here you could see that the y value associated with 5 is 3. So g of 5 is equal to 3. Moving on to part D, we need to find g of 0. So on the graph of g, we go to the x value of 0, and at 0, the y value is equal to 0. So g of 0 is equal to 0. For part E, they're asking us to find all x values such that f of x is equal to 1. So what they're saying is we need to find all of the x values that correspond to a y value of 1. So if we go to the graph of f, and go to the y value of 1 on the y-axis, then you could see that 1 corresponds to the x value of negative 2, and it also corresponds to the x value of positive 2. So for part E, our solution is written out as curly bracket, negative 2 comma 2, close curly bracket. For part F, we need to find all the x values such that g of x is equal to 0. So we need to find all of the x values that correspond to a y value of 0. Starting at the y value of 0 on the y-axis of the graph of g, you could see here that x equals 0 corresponds to the y value of 0. We also have x equaling -4 corresponds to the y value of 0, and we have x equaling 3 corresponding to the y value of 0. So we write our final answer as a set of curly brackets, and we have -4, 0, and 3 on the inside. Alright, so we're at the end of our video. Thank you very much for watching. I'm Professor Diwa, and I'll see you in the next one.